Hello guys, so this is the lecture 3 of binary heap, okay, data structure. And in this lecture, we are going to talk about two operation. One is the min-heapify and other is the max-heapify, okay. Now talking about the min-heapify, okay. So min-heapify is used to correct, okay, to correct the value in a min heap, okay, to correctly place, okay, let's just erase it, okay. So to correctly place a value in a min heap, okay. So in a min heap, to correctly place a particular value, we are going to use min-heapify function. And to correctly place a value, okay, to correctly place a value in a max heap, okay, to correctly place a value in a max heap, we are going to use max-heapify function, okay. Now let me tell you what is the purpose of these two functions. So yeah, so let's move it, okay. Now what happens is that let me give you an example, okay. So the example would be something like this. So let's say we have a heap, okay, we have a heap of size 5, okay. So let's say this is the size, this is the heap, this is what it looks like, okay. And now we have elements as 40, 20, 30, okay. And then we have, let's say, 35 and 25, okay. Now let's say these are the elements, okay. So this will be I equals to 0, this will be I equals to 1, this will be I equals to 2, this will be I equals to 3, and this will be I equals to 4, okay. Now, okay, now we have this thing, okay. This is a min heap, okay. Let's say this is a min heap. So we are given an index I in the parameter itself, okay, of the min-heapify function. We have to correct the position, okay. So at I equals to 0, there is 40, okay. But in min-heap, we know that the value of the node is less than the value of the child's, right? So child's has the value 20 and 30. So 20 should come here and 40 should be here, right? And then it should further be corrected so that 40 goes to the, the best position. Like 40 should come here, this 20 should be at the place of 40, and the 25 should be at the index 1, right? So this so the correct min heap out of this heap should be something like this. So okay, so the correct heap would be after performing min heapify, okay, obviously after performing min heapify on this heap, the heap that we are going to get, okay, and that is correct as well, is going to be something like this. So 20 comes here, 25 comes here, okay, 30 goes there, okay, and then there will be 35 and there will be 40, okay. This is I equals to 0, this is I equals to 1, this is I equals to 2, this is I equals to 3, and this is I equals to 4, okay. So this should be the correct, okay, after performing min heapify here, okay, min heapify, and we'll pass the index 0 here because the correction is needed at the index as the at the root itself, right? 40, there shouldn't be 40 but 20, right? Because 20 is having a smaller value, and in min heap we know that the minimum is at the top, so 20 is at the top, and maximum 40 is at the bottom. 40 and 35, they are at the bottom most level because they are the maximum element, they are the maximum valued elements, right? Now let's say we take an example of a max heap, okay. So let's take an example of a max heap. So let's say we have a max heap also. Let's say we take a six sized max heap, okay. Let's fill values in it, okay. Now uh, let's say we take some smaller value here, okay, 20, 40, uh, let's say 30, then let's say 60, 50, and 10, okay. Now this is absolutely correct, okay, this right part is absolutely correct, but in the left part we have to fix it, and the violation is again at the root, okay. So there should be 40 instead of 20, right? Because 40 is the maximum out of the child, right? So this is I equals to 1, this is I equals to 2, this is I equals to 3, this is I equals to 4, and this is I equals to 5, right? So 40 is maximum, so 40 should be here at index 0, 20 should be here, right? No, 20 should be here because 60 will come here, okay, and 60 will become 60 will be at the top, okay, and then 40 will be here and 20 will be at the bottommost position. So what happens is, after performing max heapify, okay, max heapify, okay, so we must remember that by max-heapify function, we can only perform the operation one time, right? We are not performing it many times so that we place each and every element at the correct position. So if we pass max-heapify index as 0, okay, so only 20 will be fixed, okay. So let's say what happens is, 20 has two childs, right? 40 and 30. The maximum value child is 40, and 40 should be at the top, right? Because the value out of the child, the 40 has the maximum value. So after the first operation, the heap that we are going to get is something is going to be something like this, okay. So it has two childs, then there are two childs of this node as well, and there is one child, okay. Now uh, let's say we write the elements, right? So 40 will come here, 20 goes here, okay, 30 will remain here, okay, 60 and 50, okay. Now again this will be fixed, right? So this is I equals to 0, okay, 10 is here, okay, I equals to 1, 2, 3, 4, 5, yeah, I equals to 2, I equals to 3, I equals to 4, and I equals to 5, okay. Now again this is going to be fixed somehow, right? So I equals to 0 here, I equals to 1, I equals to 2, okay, I equals to 3, I equals to 4, and I equals to 5. Now again here is problem, right? 60 has the maximum value in the child, okay. So what will happen is that 60 will be moving up, right? So what happens, there are two violations, right? We should place 10 here rather, okay. So what happens is, let's say there is only one violation, right? Because it will again be wrong otherwise. So let's say there is only one violation. After 20 comes here, let's say there is not 50, rather here is the elements, the value here is 10 and 15, and again we cannot have duplicates, so I'll have to replace this value, right? There cannot be two 10, right? Because then there will be no correct order. So let's say the value is 16 here, okay. Now it becomes perfect heap, okay. So 16 and 15, so now it is corrected, right? Because yeah, now the so this is going to be the correct heap after max heapifying it, okay. We are going to perform the operation only one particular time, and we are going to check for a particular path, okay. So here we checked for this path, okay, yeah, and then here we only checked for this particular path, okay, first two nodes. So this is how we are going to use max-heapify and min-heapify function. Now let's go to the code of min-heapify and max-heapify, okay, how it is going to place the correct value at a particular index, sorry, the value at a particular index to its correct value, okay, if it is not, and the index will be given to us in the parameter itself. So we'll write function something just like this, okay. So void for min-heapify, okay, for min-heapify the function will be void min-heapify, okay. Then we'll be given some index, right? So what we'll assume, we'll assume it to be smallest, because this is smallest, right? At a particular index it is smaller than its left and its right, right? In the min-heapify, that's what I told you, that the child of a particular node is having value greater than that particular node, okay, because it is a min heap, right? So let's say we take left as lt, okay, or simply we can take it as L, okay, even if we want to, yeah. So L is left, let's say, okay, it will store left of I, okay. Now for right, int r is equals to right of I, okay. And let's say the smallest, okay, smallest will denote the index of the element at which we are currently, okay. The left will be greater and the right will be greater, but we will compare, right? So if, okay, if left is less than size of the heap, and ARR of left is, let's say, lesser than ARR of smallest, okay, Okay, then what we'll do, we will change the smallest, we'll alter the value of the smallest to left. Okay, again we'll check. Okay, let's use brackets here. Okay, so that, yeah, again we'll check if r is less than size. Okay, and arr of r is less than arr of smallest. Okay, then what we'll do, smallest becomes r. Okay, smallest becomes r. Okay, now finally what we'll do, if smallest is changed, okay, if it is not equal to the previous value, we are going to swap arr of I with arr of smallest. Okay, this smallest will represent either of the either child of this I index. So let's say I equals to 0, its child are going to be, left child is going to be I equals to 1 and right child is going to be I equals to 2. So if the smallest value is present at index I, so this value at this particular index will be replaced with the index I, the left child. Okay, the value of the left child. If the smallest value is present at the index I equals to 2, then this value of I, then this value at index I equals to 0 will be replaced or will be swapped with the value at index I equals to 2. Okay, this is what is happening here. Okay, and then what we are going to do, we are going to again call. Okay, so this is going to be a recursive function. So we are going to call the min-heapify function for that particular index only, because we have to fix the value that is being swapped at that particular index to the below two values, right? So it will have I equals to 5 and I equals to 6 as the left and right child, right? So we will compare the values with these two as well. So if there is further any change going to happen, that will happen. Okay, so min-heapify of smallest will call, right? This is what going to happen. Okay, yeah, so this is all about the min-heapify function. Okay, so I already told you that min-heapify is used to correctly place a value at a particular index which is wrongly placed to its correct position. So 40 was wrongly placed at index I equals to 0, right? This index will be given to us here in the parameter itself. Okay, and then what we'll do, we'll place it at the correct position, which is here. Okay, I at index 4, and 20 will be at the top, and then 25 will be at the index 1. Okay, so this is how min-heapify function works. Okay, same is the with the max-heapify function. Only one change is there, that instead of smallest we'll take largest here as the value, and we will change the sign, this less than sign with the greater than sign. Okay, these operators with the greater than sign. Okay, so how the max-heapify function looks like, let's write the max-heapify function. Okay, so yeah, let's write it here. So int, okay, sorry, it is not going to be of any type, right? It is just going to perform its function. So it is void max-heapify. Okay, void max-heapify. Let's say we have an index given to us, int I. Okay, so int left is going to be left of I, right? This left is nothing but the function which will return us the left index. Okay, int similarly this right is nothing but the function that we declared, right, to get the right index of the right child. Okay, now we'll create another integer variable largest, which will store the index that is given to us. Okay, in the parameter itself. Now we'll check. Okay, if uh, left is less than size of the heap. Okay, and arr of left, okay, is greater than arr of largest. Okay, because largest should be the parent, right? So if it is smaller, then we'll change it to the index which is greater than it. Okay, that is L. This is L, right? This is L. Okay, and not I. So yeah, largest will be L become the largest. Okay, now if we check, if we get that r is also less than size. Okay, and a element at index r is greater than element at index largest, because if this would have been the case, right, if this would have been the case, then index would have become L. Now if the value at index r is even greater than L, then we'll again change the value of the largest. Okay, largest becomes r. Okay, the value of r becomes the largest. Okay, so largest will store the index which has the largest value. Okay, now similarly, like in the as we did in the min-heapify function, we'll again check if largest, the value of the largest changes. Okay, initially it was I, right? So if it becomes any of these two, so L, either L or R, okay, what we will do, we will simply swap the value at index with the value at this particular index at which the value is largest. Okay, simply we'll do this, and we will call max-heapify again for that particular index. Okay, max-heapify of index largest. Okay, largest. So let's try to dry run these two codes. Okay, so how we are going to dry run these two codes, let me just check, let me just tell you. Okay, so yeah, so let's see. Okay, so for the first example, okay, let's take the example of the min-heapify function. Okay, so taking the example of the min-heapify function, let's erase it. Okay, yeah, so how do we take the example of, how do we utilize it? Okay, so now let's work at this place. Okay, yeah, so what I did here is that you can see, so left becomes L becomes left of I, right becomes right of I, smallest becomes I itself. Okay, then we'll check for these conditions, and the smallest will be changed according to the value that is smallest at any particular index L, R or I. Okay, if smallest remains I itself, then there will be no change, but if it changes, then swapping will take place, and other the min-heapify function will be also called for the smallest index. Okay, now let's test it for this particular heap that I told you. Okay, so 40, 20, 30, 35 and 25. Okay, so let's take this example only. Okay, so okay, so this is the heap, right? Okay, so this is the heap that is given to us. Okay, 40, 20, 30, 35 and 25. Okay, so this is given to us. Now this is 35. Okay, this, so this is I equals to 0, I equals to 1, I equals to 2, I equals to 3 and I equals to 4. Okay, now see, this is the element at index 0 is wrongly placed, right? There should be 20 in this place because 20 is smaller than 40, right? Okay, so 20 should be at the top, right? Because it is the minimum of all the elements. So all the elements are 40, 20, 30, 35 and 25. So 20 is the smallest, and then after 20, we'll again check. Okay, so let's do this. Okay, let's dry run this code. Okay, so what I did is int L becomes left of I. So left of I is L becomes 1. Okay, left, because left of I will give the index of the left element, right? So it will be 1. Okay, now let's create the array for this particular heap as well. Okay, so that we know what is going on. So 1, 2, 3, 4 and 5. Okay, so these are 5 indexes. So at the first index, we have initially we have 40 here, we have 20 here, we have 30 here, because these are indexes, right? 0, 1, 2, 3 and 4. So at 0 index, the element is 40, at 1 index the element is 20, at 2 index the element is 30, at 3 index the element is 35, and at 4 index the element is 25. Okay, now what happens, see, according to this code. Okay, according to this code only, let's see what happens. Okay, so left, right, left is 1, right is okay, let me erase this. Okay, so yeah, now let's write again. So left is 1, left is 0 given to us. Okay, at 0 we have to fix the element, the value at 0th index. Okay, sorry, this is left and not L. Okay, left of 0, let's say index I that is given to us is 0. Okay, because we have to fix this particular element, right? The value of this particular element. So let's say the left of I is 1, right? If we use this left function that I already told you in the previous lectures, we'll get 1 here. Okay, 2i plus 1. Okay, left, for the formula left is equals to now r will be, the right will be, right index is 2, right, of 0. So right index is 2. Now smallest smallest will contain initially the index itself that is passed. So 0 will be passed, right, at the first, for the first time, because the value at 0 index is wrongly placed. Okay, 20 should be placed here rather than 40. Now what happens is, if L is less than size, so size is 5. Okay, size equals to 5, because the last index is 4, right, and size is 1 greater than the last index. So or we can say it like this. Okay, so 1 2 3 4 5, there are 5 elements, so the size is 5. Okay, so size is 5. Okay, so left is 1, which is less than size, right? So this condition satisfies. Now ARR of, whether ARR of left is less than ARR of smallest. Okay, we'll check for this. So ARR of left is ARR of 1. ARR of 1 is 20. Okay, ARR of 1 you can check here. This is ARR array. Okay, ARR. So ARR of 1 is 20. Whether 20 is less than ARR of smallest, ARR of smallest is 0. So ARR of 0 is 40, right? Whether this is true, yeah, so this is true, right? 20 is less than 40. So smallest will become L. So smallest now changes. Okay, smallest now changes. It becomes L. L is 1, right? So smallest becomes 1. Okay, now smallest becomes 1. Now again there will be a condition check. So if R is less than size, so we'll check whether R is less than size. Size is 5 and R is 2. So 2 is less than 5, right? And again we'll check for this condition as well. So whether ARR of R, which is 30, is less than ARR of smallest. Smallest is now 1, right? So whether ARR of 2, because R is 2, right, is less than ARR of 1. Let's see. Okay, so ARR of 2 is 30. 30, whether 30 is less than 20? No. So this condition do not satisfy. So we will not execute this statement. Okay, smallest equals to R. So smallest is 1 now. Okay, now what we'll do, if smallest does not equals to I. Okay, so smallest I is 0, right? This is the value that is passed in the parameter. So we'll check if smallest does not equals to I. Smallest is 1, which is not equals to 0, right? So this condition satisfies within the if block. Okay, so now we'll swap the element ARR at index 0 with ARR at index smallest. Okay, so we'll swap these two values. So 0 and 1 values are swapped, so let's swap them. Okay, so 20 will come here at the 0th index and 40 will go at the first index. Okay, so let's write the, okay, so 20 will come here and 40 goes at the index 1. Okay, now we will call, after this we'll call min-heapify for the smallest. Okay, so smallest was 1, right? So now we'll call min-heapify for 1. Okay, so the value of I is going to be 1 now, because 1 is passed in the parameter, right? So now we will again check. Okay, what we'll check now? Now we will again find the value of left and right. Okay, so let's erase this. Okay, we know that the value of I is 1 now. Okay, so yeah, so I equals to 1 now. Okay, now the left will be 2 into I plus 1. So left will be 3, right will be 4. Okay, now we'll again check. Okay, whether left is less than size. So left is 3 is less than 5, right? So again we'll check whether ARR of 3, ARR of left is less than ARR of smallest. So smallest will be I itself, right? So smallest will be I itself. So we will again check. Okay, what we'll check now? We'll check this thing. Okay, we'll check ARR of 3 is less than ARR of 1. Okay, so ARR of 1 is 40 and ARR of 3 is 35. Yeah, so 30, whether 35 is less than 40, so the condition is true. Okay, so what happens is smallest, the value of smallest was 1 earlier. Okay, it was 1 earlier, but now it gets changed. Okay, so what happens is the value of smallest changes to L. Okay, so L is 3 now. Okay, after this condition satisfies, right? This condition satisfies. Okay, now we'll again check. Okay, we'll check for right index as well. Okay, so let's erase this. Let's erase all of this. Okay, we'll again check whether R is like, the value of R is 4, right? Whether 4 is less than the size is 5, right? So this condition is true. Okay, now we'll check whether ARR of R, which is ARR of 4, right? ARR of, what is the value of ARR 4? The value of ARR 4 is 25, right? So we'll write directly here. Okay, ARR of I. Okay, sorry, it got erased, or simply, yeah, whether ARR of right, okay, right is 4, right, is less than ARR of smallest is 3 now, okay, after this condition executed, right, after this statement, if statement, okay. Now we again check, okay, so ARR of 4 is 25, whether 25 is less than ARR of 3, ARR of 3 is 35, yeah, so this condition is true, right? So smallest will again change, okay, the value of the smallest changes again, and it becomes R is 4, right? So smallest becomes 4. Now what happens is that if we'll check for this statement now, last if statement, if smallest does not equals to I, so I was initially passed as 1, right? So if smallest, which is 4 right now, after the swapping, smallest becomes 4, 4 is not equals to the initially passed thing, which is 1, right? So what we'll do, this swap occurs, okay, this swap thing occurs. So what happens is that we swap ARR of I, which is 1, with ARR of smallest is 4, right? We'll swap these two, okay. Now let's swap, okay, let's swap the value here, okay. So ARR of 4 is swapped with ARR of 1, so 25 comes at index 1 and 40 goes at index 4, okay, yeah, so 25, okay, okay, so 25 comes at index 1 and 40 goes at index 4, okay. So yeah, so now we get the array this way, okay, and now we're going to call min-heapify of smallest was 4 now, right? Okay, if we call min-heapify for 4, uh, its left will be 2 into 4 plus 1, right, and its right will be 2 into 4 plus 2, okay. So the left index of this 4 is going to be 9, and the right index of 4 is going to be 10, okay, both of which are greater than the size, okay. So smallest do not change, and if smallest do not change, then this statement will not be executed, and this is going to be the final answer, okay, this array is going to be the final answer. Now when we, if we try to represent it in the form of a heap, what heap do we get, okay. So let's see, let's create a heap, okay. So the size is 5, let's create a heap here, okay. So let's say this is the heap, okay, this is the heap. Now after adding the elements, this represent index 0, right, this represent 1, this represents 2, this represent index 3, and this represents index 4, okay. Now 20 will be stored at index 0, 25 comes here, 30 comes here, 35 comes at index 3, and 40 goes at index 4. So this is the correct min heap, right? You can check, okay. So this is the correct order of the min heap, right, after using min-heapify on this previous heap, right, we are getting the final heap as this one. So yeah, and now we can check how, because in min heap what happens is every node has a value smaller than the value of their childs. So let's say for I equals to 0, the value of child is 25 and 30, that are both greater than the value of node itself, which is 20, right. And now for this node, it has childs, right, so we'll check for this node. We'll not check for this node because there are no child of this node. So for this node I equals to 1, the value of the childs are 35 and 40, both are greater than 25 itself, right. So this is what it states that it is a min heap, right. So this is how we get the correct min heap after using the min-heapify function, okay. So yeah, this is something that is important, and you have to remember this for functioning of the min-heapify function, okay. So that was it for this lecture. Hope to see you in the next lecture, where we are going to talk about the max-heapify function, okay. And it is also an important function to fix the heap when the heap is a max heap, right. So that is it for this lecture. Hope to see you in the next lecture.